Now, I can hear you wondering why we don't simply use a calculator. But what is the calculator doing? How does the calculator compute a number? Well, the calculator is using linear approximation as well, often through the following algorithm. Newton's method is an algorithm for finding the root of a function, f of x. The first step in this method is to guess. Pick some value, let's call it x, where we can compute the function and its derivative. Then let's say that the root is nearby at some value x plus h for some h. We're going to linearize f at x to get f at x plus h equals f of x plus f prime at x times h plus terms in big O of h squared. Ignoring those terms and approximating, we can solve for the root. Set that equal to 0 and solve for h. And that gives us minus f of x over f prime at x. Now h is not the root. X plus h is the root. And so we get the following formula. And the genius of Newton's method is not to stop there, but to repeat or iterate and do it again, getting a better approximation. And then your last step is to hope that this repetition will converge to the desired root. So, if you zoom in on what's happening, we linearize, solve for the root. Then we do it again. We linearize at that new point and then solve for the root. Keep your fingers crossed. This may converge. Now, let's introduce a bit of notation. Our initial guess we will call x naught, that is x with a subscript 0. Doing the linearization and solving gives us an update rule. x1 is equal to x naught minus f at x naught over f prime at x naught. And the repetition gives us a sequence of points x sub n, where the next term in the sequence, x sub n plus 1, is given by x sub n minus f of xn over f prime at xn. This is Newton's method. Now, hopefully, it converges. Let's consider the problem of trying to compute the reciprocal of a number, a. 1 over a can be realized as the root of f of x equals a minus 1 over x. What would it take to compute that root? Well, the derivative of this function is easy to compute. It's 1 over x squared. And taking Newton's update law, substituting in for f and f prime, and doing a little bit of simplification, gives that x n plus 1 equals twice xn minus a times xn squared. What's remarkable in this formula is that there's no division involved, only multiplication and subtraction. So let's fire up the computer and see if we can't solve this for a value of a equal to e, 2.71828, etc. We'll make an initial guess of x naught equals 1/2, and then we'll start computing using Newton's update law that we have derived. And what we see is that after a few short steps, just 4 steps, seems to be giving us 6 digits of accuracy. That's pretty good convergence. Likewise, if we want to compute a cube root of a, we can realize that as the root of f of x equals x cubed minus a. In this case, also, the derivative is trivial to compute. And inserting these into Newton's update law gives us xn plus 1 equals 2/3 xn plus a over 3 times xn squared. Now again, if we, say, evaluate this for a equals 100, what's the cube root of 100? We need to make a guess. I know that the cube root of 125 is 5. So let's use that for our initial guess. And then doing the computations gives a value that seems to be converging extremely quickly. Even after 3 steps, we've got as many digits of accuracy as represented on this computer. So what we see is that sometimes Newton's method converges very quickly. But other things can happen. You have to be careful. Let's say you pick an initial condition and start applying Newton's method. One of the things that can happen is that you do not converge to the root you wanted to get. You may converge to a different root. Worse things can happen still. Depending on your initial condition, you might wind up getting a value of xn for which the derivative there vanishes. As you can see, either graphically or from the update law, this leads to a situation where xn plus 1 is undefined. And this is really bad. You might not converge to anything. But despite those dangers, Newton's method and linearization are extremely useful in practice. Linearization pervades mathematics, and there are all manner of things that you can linearize. You can linearize data. You can linearize differential equations and dynamics. You can even linearize operators. We'll get to a little bit of this later on in this course, but some of it is going to have to wait for you to take more math.
And so we see the power of linearization, of using the first derivative to approximate. But this is really just the first step in a broader Taylor expansion. In our next lesson, we'll consider higher derivatives and their uses across a variety of applications.